Instead of creating the model from scratch, we're going to start with the one created in the planar shell bending tutorial. Let's rename the model Plastic Plate Bending Model. We will modify the material AISI 1005 steel, created as part of the original model. Let's rename it Steel, since we will only use a generic yield stress versus plastic strain curve for steel. Change the Poisson's ratio to 0.3. Create a new plastic material behavior by opening the mechanical menu and choosing plastic from the plasticity menu item. Type in the yield stress versus plastic strain data for the material. As you fill out each cell, hit the Enter key on your keyboard to move to the other cell. It's possible you have your yield stress versus plastic strain data in an external file, and typing it out into this table is tedious. There's another way of getting this data into the table. Clear the contents of the table by right-clicking in any cell and choosing Clear Table. I have the tabulated values in a text file with a tab separating the stress from the strain, and each stress-strain pair on a new line. Right-click in any of the cells and choose Read from File. Click the Select button and navigate to your file. Notice that below the file name, Abaqus tells you that the fields can be delimited by spaces, tabs, or commas. In our case, we have tabs separating our stresses from strains, and Abaqus will be able to identify the two separate columns thanks to the tab delimiter. We tell Abaqus to start reading values from our text file into the first row and first column of the table. Click OK. Abaqus populates the table with the values from the file. If you want to visualize the yield stress versus plastic strain curve, you could plot it in a tool like Excel or MATLAB. But there's an even easier way to do it in Abaqus. Right-click anywhere in the table and choose Create XY Data. Set the name of the XY data to Steel Stress versus Plastic Strain. Since we want plastic strain on the x-axis and yield stress on the y-axis, we tell Abaqus to read the x values from column 2 and the y values from column 1. Click OK to close the Create XY Data dialog box, and click OK to close the Edit Material window. Abaqus informs you in the message area that the XY data has been created. Switch to the Visualization module. In the results tree, expand out the XY data container and double-click on Steel Stress versus Plastic Strain. You see the curve plotted in the viewport. We can modify the appearance of the curve to reveal the data points. Use the XY Curve Options tool. In the Curve Options dialog box, set the line style to dashed. Check the Show Symbol option to display the data points. We will change the symbol to a diamond shape and the size to large. Click Dismiss to close the dialog box. You now see the curve with our yield stress versus plastic strain data points. Notice that Abaqus has interpolated linearly between these points, hence you see straight lines connecting them. Abaqus Standard will use the user-supplied data where possible and the linearly interpolated values for all the intermediate points when running the simulation. It makes sense, therefore, that the more points you provide, the more accurate the representation of the material plasticity. Abaqus Explicit, on the other hand, will regularize the data for the sake of efficiency. In layman's terms, this means it will generate stress-strain data points that will form a nice smooth curve. However, it is possible that the points it generates may not coincide with the original user supplied data points. Abacus Explicit will attempt to generate a sufficient number of intervals so that the maximum error between the regularized and user supplied data is less than 3%. Also note that Abacus will not attempt to project your curve beyond the last point. The stress is assumed to be constant outside the range defined by the data supplied, hence the curve is perfectly horizontal after the last supplied data point. This means that the stresses in the material will not exceed the stress of the last stress strain point on the curve, and once the stress in the material reaches this value, the material will deform continuously until the stress is reduced below this value. Hence, you must check to make sure that the stresses in your model never reach this portion of the curve, or your results will be meaningless. Material test data is often in the form of nominal stress and strain, and I want to take a moment to explain how you would convert the nominal stress strain to true stress strain data that Abacus can use. You find the true stress from the nominal stress and nominal strain using equation 1. The true strain is found from the nominal strain using equation 2. Since the strains obtained from the test data are probably not plastic strains, but rather the total strain, this total true strain needs to be decomposed into its elastic and plastic components. The true elastic strain is obtained from the true stress and the Young's modulus using equation 3. The true plastic strain can then be found by subtracting the true elastic strain from the total true strain as shown in equation 4. Now let's change the initial increment. Abacus Standard solves a problem by applying a fraction of the load in an increment, solving the system of equations, and iterating till convergence, and then increasing the load in the next increment. This procedure is repeated till the final increment when 100% of the load is applied. Currently, our problem is set up so the entire load step occurs in one increment. However, in a nonlinear analysis, it is almost always better to set smaller increments. This is because the solver is unlikely to converge to the solution when it applies the entire load in one increment, and will internally do a cutback and try to solve with smaller increment size. For highly nonlinear problems, Abacus Standard might have to reduce the increment size repeatedly. This wastes computational time. Hence, it is preferable to have multiple increments from the beginning in any nonlinear problem. The way we can achieve this is by setting the initial increment to a fraction of 10%. So, if your step time period is 1, set the initial increment to 0.1. This means that the solver will apply 10% of the load in the first increment. Abacus will automatically adjust the sizes of subsequent increments based on the convergence behavior of the solution, hence you only need to specify the initial increment. It is hard to determine exactly what will be a good initial increment, and Abacus will in fact let you change even more options, such as limiting the minimum and maximum increment sizes, as well as the total number of increments. However, an initial increment of 10% is generally assumed to be a good starting point unless you have already run the simulation previously and examined the status file. Double-click on the load step in the steps container to see the edit step window. You see that the step time period is set to 1. Switch to the incrementation tab. Here you see the initial increment size is also set to 1. Since the initial increment size is the same as the total time, Abacus will attempt to solve the problem in one increment. We shall change this increment size to 0.1. Abacus will now apply 10% of the load in the first increment. Note that time has no physical meaning in a static analysis. It is only meaningful when comparing it with the initial increment. So you could instead set the step time to 5 and the initial increment size to 0.5, and it would mean exactly the same thing as setting the step time to 1 and the initial increment size to 0.1. Now let's modify the loads. We will change the concentrated forces to 270,000 newtons in the negative y direction. The model is now almost complete. We will create a new job for this analysis, If you already have an existing job, you can delete that. We shall call our new job Plate Job Plastic and set it to solve the plastic plate bending model. The job type is set to full analysis. Run the job by right-clicking on it and choosing Submit. Abacus warns you that history outputs have not been requested. Click Yes to continue. You see that the job has been aborted, and Abacus tells you about errors in the message area. The important one among these is that Abacus was unable to find the material AISI 1005 steel. Since we modified this material and changed its name to just steel, it is apparent that some part of our model is still referring to the original material and has not been updated. It is likely the section property. Right-click on Plate Section in the Sections container and choose Edit. Abacus informs you that this section refers to the material AISI 1005 steel, which no longer exists. Since the new material steel is the only material in our model, it is now the only one displayed in the drop-down menu. Click OK. Let's try to run the job again. This time it goes through till completion. Let's view the results. Plot a contour on the plate. The Mises stress is displayed by default in the legend. The text of the legend appears quite small on my system, so I'm going to increase the font size to make it more readable. In the Viewport menu, click on Viewport Annotation Options. You get the Viewport Annotations Options dialog box. Switch to the Legend tab. Click on Set Font. We will leave the font set to Verdana and change the size to 14. Notice the legend is checked in the Apply To section. This means our change to the font size will apply to the legend only. We could in fact set the font of the title and state blocks from here too, but we'll do that from the Title Block tab instead. Switch to the Title Block tab and click Set Font. This time we will change the font of the title block and the state block. Set the size to 14 and change the font to Times New Roman. Also check Italic. You see the changes to the font in the viewport. Now let's talk about restart analyses. As mentioned in the overview, a restart analysis allows the user to continue an analysis from where it stopped. The analysis may have stopped because it was unable to converge, or the maximum number of increments for the step was reached, or the computer may have run out of disk space or crashed. It's also possible that the analyst intentionally wished to separate the steps of the analysis into separate jobs so that the results of each step can be viewed and the validity of the solution till that point can be confirmed. In all of these cases, a restart analysis will allow the solution to continue from where it left off. It is also useful for transferring results between Abacus Standard and Abacus Explicit. Let's take a look at the files generated by Abacus during the analysis. These will be in your Abacus work directory, which by default is in the temp folder in the C drive. In my case, I have it set to a folder called Abacus Temp in the C drive. You see a number of files here, and you have likely noticed these being generated every time you run an analysis job in Abacus. The file we are looking for is a restart file with a .res extension. This is a file that can be used to continue an analysis. However, no restart file is present. This is because Abacus Standard does not generate a restart file by default. It needs to be specifically requested. So let's return to Abacus and request restart output. Switch to the step module. From the output menu, choose Restart Requests. You see the Edit Restart Request dialog box. It has a table listing the steps of the analysis, the frequency and intervals at which restart data should be written, and options for overlay and time marks. Restart output is written for the steps requested, not the entire analysis. The analyst has two options for specifying how often restart data should be written. If a frequency n is specified, then Abacus will write the results after each increment whose increment number is a multiple of n. So the restart data is written every nth increment. In addition, the restart data will be written at the end of the step. If an interval m is specified, then Abacus Standard will divide the step into m time intervals and write the requests at the end of each interval. When specifying an interval, the checkbox for time marks will become available. If the analyst checks time marks, the results will be written at those exact time intervals, whereas if time marks is left unchecked, the results data will be written at the increment ending immediately after each time interval. The frequency option is available only in Abacus Standard, whereas interval is available in both standard and explicit. Change the frequency to 1. This tells Abacus to write the restart data at the end of every increment. The checkbox for overlay becomes active. This option allows you to tell Abacus whether the restart data written at the required increments should be appended to the restart data written at previous increments. We are going to check overlay, so every time Abacus writes restart data, it will replace the previous data. So even though we are writing restart data at every increment thanks to our frequency of 1, we only hold on to the latest set of restart data. As mentioned before, Abacus will write restart data one last time at the end of the analysis step. Since we are overwriting previous restart data, we are basically saving the restart data at the end of the load step. The overlay option is useful because the analyst cannot specify what data is written for the restart. Abacus writes a complete set of data each time, so it is possible for your restart file to get quite large. Saving only the last set of data alleviates this issue. You might ask why we are writing the restart data at every interval anyway, if all we need is the one at the end of the step. The answer to that question is that quite often restart data is written so an analysis can be restarted after an error or crash terminates the simulation. It is not known at that point what increment this error will occur at, hence you specify a frequency or time interval of sufficiently small size that your restart point is quite close to the point the simulation terminated. Of course, writing restart data to a file itself takes time, so in a large simulation you should avoid writing restart data at every increment as we have done here, and should instead pick a lower frequency.